Last episode I drew the RAG loop and said two foundations hold the whole thing up: how you chunk the documents and how text becomes a vector. Get either wrong and no amount of clever ranking saves you. So let's build both. And the magic line is this: in retrieval, meaning becomes distance. Start with chunking. You can't retrieve a 400-page PDF, you retrieve a paragraph. So how you cut the document decides what the system can ever find. Cut too big and the one relevant sentence is drowned in noise and blows your token budget. Cut too small and you lose the surrounding context that made the sentence mean anything. It's a Goldilocks problem. The strategies from crude to clever. Fixed size, n tokens with overlap, ignores structure, splits mid-sentence. Recursive, try to break on paragraphs, then sentences, then words. This is the pragmatic default. 512 tokens with 50 overlap covers most apps. Semantic, start a new chunk when the topic shifts, best recall but slow, because you embed every sentence. And parent document, retrieve a small precise chunk, but feed the model its bigger parent for context. Rule of thumb, factoid questions want small chunks, analytical questions want big ones. Now embeddings. An embedding model turns text into a point in a high-dimensional space, arranged so similar meanings land near each other. Refund policy and how do I get my money back become neighbors with 0 words in common. Once meaning is geometry, search is just embed the question, find the nearest points. The model that does this is a bi-encoder. It encodes the query and the passage separately. That separateness is the whole trick. You embed all your passages once offline and only the query at runtime. That's why vector search scales. 3 properties to know. Dimensionality, typical sizes are 384, 768, 1024, 2048. Bigger is more expressive but costs storage and slows search. Normalization, L2 normalize the vectors, so a dot product equals cosine similarity. And Matryoshka, a model trained so you can chop a 2048 vector down to 1024 or 768 and still retrieve well, trading a little recall for speed without re-embedding. NVIDIA's NeMo retriever embedding names do all this, and they're asymmetric. You must pass input type, query or passage, so the model applies the right prefix. That's the detail people miss. Let me show it in code. Chunk a document recursively, embed the chunks and a query with an NVIDIA embedding name, and print the cosine distances so you can literally see meaning become distance. First, chunking, recursive character text splitter, chunk size 512, overlap 50. It tries paragraph breaks first, then sentences. Watch the terminal. One document becomes clean passages, no mid-sentence cuts. Now embed the passages. NVIDIA embeddings pointed at the embedding NIM on a port 8080. Note input type passage, this is the ingest side. The terminal shows the vector dimension, 1024 floats per chunk. Embed the query with input type query, the asymmetric bit, a different prefix, then cosine similarity against each chunk. Look at the scores. The refund chunk scores 0.89, the store hours chunk 0.12. The question and the right passage are neighbors. The irrelevant one is far away, meaning became distance. We can turn a corpus into vectors and a query into a vector and find neighbors by cosine, but over millions of vectors, comparing the query to every single one is far too slow. You need an index, and ideally one that runs on the GPU. Next, flat, IVF, HNSW, PQ, the 4 databases, and CUVS. Thanks for watching. Like and subscribe for more videos like this, and I'll see you in the next one.